So this is almost up to date, but not quite. And the up to date part, we get it tomorrow for the satellite data, and maybe we'll know a bit more from Siemens in situ TAC what's happening in the buoy, but it's in progress. So it's impossible to talk to you about all the possible source of data there is. So this is a very personal view on this, where to find the some data, and what exists and what you can do. So for buoy data, maybe you have your own buoy. There's many public bodies around the world that are deploying and maintaining and distributing some buoy. Some are completely public, and this is why it's easy to find and use. And so I've mentioned here NDBC is the National Data Buoy Center in the US, which is operating buoys around the US coast. CDIP, which is a joint program between the US Army Corps of Engineers and the University of California, San Diego, actually operates buoys in many different places, mostly around the US, but not only. There are buoys across the Pacific. They have a few buoys in funny places. And so CDIP, also what they do is actually they provide a service to put data available for people. So there's actually some university like Hawaii, they actually own the buoy, but they let CDIP process the data. And NDBC also processes data from other institutions like Woods Hole has some buoys in the South Pacific. There's like one buoy of Peru, another one of Chile, which all data is reviewed by NDBC. So if you actually go to the NDBC website, this was I was showing just before, NDBC, NOAA.gov, and on NDBC you will also find the position of the CDIP buoys. And so this is basically all the platform they have. So it's not all waves, right? It's all these tropical stuff is just for currents and meteorology. But if you zoom in and look for wave buoys, you will find some. And you will also find the real-time data from a few other platforms, like the French buoys. In real time, they're reported there. You don't find the historical data, but you can find the real-time data there. And so what I used to do before Siemens arrived and GlobeWave, I had the automatic cron tab parsing through the web page to get the data and then store them. And hopefully now you don't have to do that anymore, but that can be a nuisance. MEDS is a Canadian system, which has buoys that are similar to the NDBC buoys. Put here CFAS, which is a UK fisheries and whatever. So they have a lot of coastal buoys around the UK. There's the Italian Rete Onda Metrica Nazionale. At some point it was possible to get the data. Maybe we can talk. I don't know where that is.
No, I think that there's no more on the Rete Onda Metrica Nazionale. It's no more working.
Okay.
But there are several years. Let's say I spoke with LAM, with you guys from LAM.
Okay.
They said that it's dead basically because they have not found again. They have no money.
So yeah, so it's hard to keep track with all these buoys around the world, and some of them are semi-public, so it's not always easy to find. And again, there's especially at NDBC, there's a lot of variation in the quality of different sensors from different buoys. The good thing with CDIP, it's all data wave riders, so you know what to expect, but the other ones, can be very different. And finally, there's hope is on the way, and the Copernicus Marine System is going to provide all that for us. I guess that's coming. And I'm really encouraging people to make their data available for different things. So we're getting some data as part of the, there's an exercise of model validation and comparison, which is run by Jean Bidlot at ICMWF. But so I have the data, but I cannot distribute it because some people, like Australians, are providing data from harbors, and so it's actually not owned by the government. It's actually owned by each different harbor, so it's there's data rights that are a problem. The satellite data on the paper, it's much more easy, and it's really getting easier every day. So we have different types of data. We have satellite altimeters, which measure wave heights. And I should have explained how, but normally Fabrice Collard will tell you all that tomorrow. So if you want to know how it works, he will tell you that. But basically, we're getting significant wave heights from the satellites. We're also getting some other funny parameter, which is called the mean square slope. from which you could combine these two and get some proxy for the wave period, but yeah. Let's just look at the wave heights now. We also have some other sensors which are making images on which you can see the waves, and these are synthetic aperture radars, or SARs. And what I don't have here is that soon we'll have CFOSat, which is yet another type of measurement. As I said, we're working a bit with seismic noise, and soon we should have actually a database of spectra as part of the GlobeWave CCI, of the C-State CCI project. And there's also people watching waves from the ships, and there's a voluntary observation ship program which is reporting data to the WMO, the World Meteorological Organization. And there's colleagues in Russia that have done a lot of work in cleaning up that data set, and it's a very impressive work because it's actually going back almost 200 years of data. And it's work done at Chershov Institute in Moscow by Gulev and his group. And it's all available on the website. You can download it. So we have essentially measurements at ship positions that go back a long time. That's pretty much what exists. So this is observation. There's a lot of people are running models. So as you will learn and to do it yourself, you can also do your own next week. So models of ocean waves are driven by ocean winds. Winds over the oceans. And there's many different hindcasts. Some of them are made by private companies for profit. So Ocean Weather used to make a lot of money from oil companies by making special wind fields to drive their special wave model. These days, I don't know how much that they're doing, but maybe for special high-resolution things. ECMWF has been producing reanalysis, so this is called the European reanalysis era. So there's one called ERA Interim that a lot of people have used, but I can warn you directly that it's not very good for waves because the winds are a bit too low, and I will show you some example. Geez, I didn't put a slide now. There's a very nice paper, if you want to know all the details about that, by Justin Stopa. So it's Stopa, S-T-O-P-A, it's an ocean modeling, and it just came out this year. So what Justin did is actually compare 8 different reanalyses for winds and discussing the quality of the winds and the waves you get from that. The one we used a lot is a climate forecast system reanalysis from NCEP and NCAR. It's actually a 2-phase project. There was a V1 reanalysis up to 2010, I believe. And then now they do reanalysis and rerun, the version 2, in which actually every month they produce data which is consistent or supposedly consistent with past reanalysis. The group in Cantabria of this global ocean wave, I believe, called GO thing. The Canadians do some stuff. There's some other French group do some other things. And we've done our own, so that was the name of the project for the integrated ocean waves and geophysical applications. So it's what we have on the FTP, and so we do global, we do regional. So that's the hindcast. If you're looking at forecast for tomorrow and the coming days, there's even more. I will show you. There's a joint commission on oceanography and marine meteorology workshop. Work group which is working on comparing different model forecasts, and so I think now there's like 15 different centers contributing to that, and the quality varies a lot, and it's mostly driven by the wind. And if you want to look back in time, one issue is going back before 93, and the reason for 93 is that going back up the way to 93 were satellite altimeters to tell us, if the wave heights are good or not, which is the main quality check we do on the wave models. If you want to go back before 93, then you're on your own. You want to have a few buoys to tell you if the model is good, and that maybe it's going to be good in the US and not good in the Southern Ocean, and it's hard to tell. So this is also where we're starting to use seismic noise. And so what I will focus on here is what we actually use here and produce here. I'm not going to cover all these different things because it's just too much to keep track of. So the buoys, this is pretty much what the buoy network, or the network of buoys that I can find the data look like around the European coasts. So there's maybe a couple hundred of buoys, and so I think more would be nice. There's this nice network in the Azores. There's some buoys maintained by the Hydrographical Institute in Portugal and so forth. It's not always easy to get to this data, and I'm pretty sure actually all of these are already in the CMEM stack, I mean, like maybe even more than that. And so actually, maybe this afternoon you could show us how to access that in practice, or whatever.
I have a poster to bring back from my office.
Wonderful. So you will see we'll learn from the data people. That's on the US side. So on the US it's easier because the CIP and NDBC are remaking and the Canadians are making some effort to make it nice and easy to use. And there's some other places. This is the stuff that's hard to get, and we're getting through CMWF as a part of model validation, and so forth. The Australian and New Zealand buoys, but most of the world has really no buoy, like all around. So there's some buoys off South Africa which are maintained by CSIR from Stellenbosch in close to Cape Town, but the data is not public. And from other African countries, I'm not aware of buoy data. I know there's one buoy of Mauritius from the Mauritius Institute of Oceanography that's in the Indian Ocean. But there's parts of the world with it's really not easy to get. And I know in Chile there's like a couple of buoys from the Navy, but it's not public. Satellites. So you will learn much more tomorrow, but this is about all the satellite altimetry missions. So the first demonstration that you could measure wave height from a radar on a satellite was done with Skylab in 1973. It lasted for a few months. That data is not yet available, as I know, but we'll try to get that. Then there was GEOS, CSAT, and actually most of the data easy to get and use restarts in 1985 with GeoSat. And GeoSat lived until 89, and then we have a gap. And then the continuous record starts in 92, actually, there's a launch and then the commissioning phase of ERS-1, the European Remote Sensing Satellite. For quite a few years, we had two satellites with ERS-1 and TOPEX. Then ERS-2 was launched, and we are here. We are 2018. We're here today. So today, I think we have 7 satellites flying. What the latest launch was Sentinel-3B. Yes, which was indeed launched in 2018. So right now we have JSON-3, Sentinel-3A and 3B. So 3 and 3B are on the same orbit right now, but they will be shifted soon to actually get more independent data. Right now they're just one behind the other with a 30-second difference to make sure that they're measuring the exact same thing. Cryosat-2 is working. HY2A, that the Chinese altimeter, is also working. SARA LTK is also working. So it's 1, 2, 3, 4, 5, 6, and which is the 7th one? I don't remember, but I think there's 7. So there's a lot of data, but it's still not enough. Still not enough because if you have one. For a given day, this was from which date? Yeah, 2009, January 2009. I think there's 4 satellites on that one. You can see that in one day, if you're not lucky, like you want to know what the wave here, you have no data at all during the full day. And the waves change, of course, on a time scale of a few hours. And so in a day, you can have a storm or completely miss it. So here you see some tracks go. The red is very high wave heights. Which are crossing here somewhere in the Southern Ocean. You have some storms here, but maybe there's a storm here that nobody has seen, and that's life. So we have lots of data, but if you actually want to do work exclusively based on satellite data, you can do statistics or long term, but you cannot really say much about what's happening from one day to the next day. This is some coverage of some SAR data. So, SAR data is always hard to look at, but these are some examples of radar images coming from this region here, and some other radar images. And you see all these small dots here on the map are this kind of square images, 20 kilometer by 20 kilometer. And if you actually could watch my screen, you could see the waves on top of this. So you have this kind of wavy pattern there. When you make a spectrum of that, you get this. And you actually have a spectrum with two different systems with some long swell and short swell here. And that's a typical coverage. Also in, I think, probably a day, you get this kind of map now with Sentinel-1A and Sentinel-1B. And this is only since 2014. Before that, we had a gap. MVSat was giving data until 2000. When was it? 12? No. Maybe. MVSat died, yeah, 2012, and then Sentinel-1A was launched in 2014. So we have two years without any swell data from SAR. But there's some swells, and we're working on that. A few words about seismic noise. This is just a subset of the high-quality seismic stations around the world in 2013. So basically, any small island anywhere has a seismometer on it, and there's even more these days. And these things record background noise. And this is the measurement of the seismometer. This is the energy in color as a function of time and frequency. And if you had a buoy of these, so this is coming from where? Which station is that? Don't remember. So quite possibly it's in the middle of France, near Saint-Étienne. But it could be anywhere. And so if you had a buoy in the ocean that would measure something very much like this, and we can actually model this signal. So this is the model of that based on the wave model. We can actually simulate what is measured by seismometers and try to invert that to get some wave measurements. So it's still research and work in progress, but it's going to happen. And so in some cases it works really nice. This is off California. You have a very nice relationship between the seismometer data in Berkeley and the oceans and the ocean waves in the ocean. This contour map shows you basically the region to which the sources are coming from. So this station is sensitive to sources along the coast. And you can actually correlate you can actually do some statistical estimation of the wave height from the seismometer, and it compares pretty well to wave height from the seismic station. So that's special for California. If I do that in France, it doesn't work so well because the source is coming from more other regions. So that's measurements and hindcasts. So actually, what we do here in the lab, we actually develop the wave models. We're changing the parameterization, how we compute the wave generation and dissipation and other things. So we work a lot on the parameterization. So you can go to these. These are papers about wave breaking and dissipation. There's more now about the ice. And we actually test our model in forecast mode. And so we're part of this JCOM model comparison verification. And this is typical scores of scatter index as a function of forecast range. So 0 is the analysis. So you have the observation and you're running the model right now from the wind. And 5 is like you have a 5-day forecast for the wind and you're looking at the 5-day forecast of the waves corresponding to this wind forecast. So you can see that the scatter index or the error is growing in time. Okay? And the different colors are different forecasting centers. So the red one here is ICMWF. The dotted one here in blue is a model we run here, and the dashed purple one is Météo France. So that was a plot from a couple of years ago, 2016. This is winter, and this is summer. And you can see that in summer, in 2 years ago, we're actually getting better forecasts, and Météo France also, compared to ICMWF. And the reason is basically because we have different parameterization. So we use the same wind. We use ICMWF wind. We make a forecast with a different model than their model, and this is showing the impact of essentially the breaking and swell dissipation in the model. And the other ones are this one is NCEP, NOAA NCEP. The dashed one here is the Bureau of Meteorology. This is the Australians. The German DVD, the whatever. So you can actually find all these plots on the JCOM website if you search for them. And these days, our forecasts are not so good. I think we have some problem with the wind forcing. So Michael is, we're trying to figure out what's going on. So that's the, so this is actually, so this is comparing the buoys on the global scale. So we take all the buoy data around the world, mostly from NDBC and CDIP, but a few other ones. And we compare the model to the buoys, and we look at these kind of plots and the scores. That's at the global scale. So we also work a lot in coastal areas. So we had for different applications, we developed this model for the French coast. So we use a triangle mesh, so kind of stuff you will see next week. So you don't see it very well, but you can see that you have big triangles here, so it's kind of gray, and then it goes to small triangles close to the coast. And so we're covering the Spanish coast all the way to the Dutch coast. So that was this domain we call Norgas UG, or unstructured grid for the North Sea and Bay of Biscay. The special thing about this this model setup, it's using bottom friction, which varies with sediment types. So this map is a map of the grain size diameter, the median grain size diameter. So the red means it's essentially rock and pebbles and gravel, and the dark blue is silt and mud, and the fine sand is around the like bluish or green colors. And so these different changes in bottom types actually is very important for bottom friction. And for example, here on the coast we have places where the shelf is 20, 30 meter depths, and so that's where it's really important. And apart from that, so we've been running a hindcast with this grid, so it's 200,000 node mesh or 150,000 node mesh for 30 years hindcast. And so it's used a lot for marine energy applications, stuff like that. We also use it in forecast mode, and now Météo France is using basically the same grid for forecasting storm surges and maximum water levels. And the next project that Matthias will be involved in is actually we'll extend that grid to Portugal all the way to Norway with, I don't know, 500,000 nodes, and run that for 30 years, and so people will have fun. And hopefully, by the end of next week, you'll be able to make this kind of mesh and do it yourself. That's the plan, if you want to do that. So the reason why we did this hindcast, so as I said, we have a different quality of the forecast, so we know that the parameterizations of the braking and dissipation can be better. And also, we know that the wind is making the waves, okay? But it's not just the wind. At some point, the currents are very important, especially at scales less than 100 kilometers. So if you want to go to high resolution, you really need to put in the currents. And also what we did in this global hindcast, we also included the effect of icebergs, because in Southern Ocean, there's actually lots and lots of icebergs, and they block the wave energy. And so that's really important to get the Southern Ocean wave climate. The other reason why we did this hindcast is also because many people that do look at drift, like plastics, or look at air-sea mixing, there was no available database for proper variables. So we actually output from the model all sorts of possible variables for computing these parameters. And then the last bit was for doing this high-resolution coastal stuff. So we actually have, I could actually pull it up. So all of that is available on the IFRAMER FTP. And we will be playing with some of that to get some example. So it's this hindcast. It is working. Okay, so this is working. And the FTP, yes. So the way the hindcast is organized, it's organized by regions. So you have a global folder in which you will find all the global hindcast results. So there's basically here it starts from 1990 all the way to this year. And you see you have this extension for different wind forcing. So we've run both with the CFSR winds, the climate forecast system reanalysis, and ECMWF corresponds to the ECMWF operational analysis and forecast, not the ERA interim. So it actually is better quality for the recent years. And in some cases, and it's what we'll be doing more of that in the future, we also use aviso currents, so currents derived from altimetry to also take into account wave current interactions. It turns out that these currents are a bit too smooth, and so the gradients we get in wave heights are not yet what we would hope for, and there's actually a poster about that if you want to look at, we can discuss. So we have all that here. So there's a global folder, and then you have other regions like the There's Arctic hindcast, which is it's on the Carolina grid covering the Arctic, going from 92 to 2016. It's actually described in a paper we did with Justin Stopa. And things like the Mediterranean Sea and the Northwest Atlantic, for example, would be the same. So it's actually a grid inside of this system. And so for each folder, then you can go in and you have all the different variables. We made it separately. At some point, we probably will have to move to some opened up and more easier access to things. But right now, you can just click and download the different variables you get. Go to HS, and then you just have the maps of wave height. So monthly files with maps every 3 hours or 1 hour, depending if it's coastal or open ocean. So that's the way it's organized. Yes, and so there's basically, whoops. There's one system which is coming from this global grid with nested zooms inside. And then we also do some special runs with and without reflection of the waves at the coastline. And that's, most people don't care about it. This is specifically for seismic noise analysis, so we work for seismologists. And something we also have expanded recently is also including infragravity waves into the model. So instead of starting usually at wave period around 20 or 33 seconds, we actually go to longer periods. And this is still in development, but there's a hindcast of 4 or 5 years already available there. So far, we're using the version 5.16 of WaveWatch, and so all of our grids had the same number of frequency and directions. So you can play with that. You could go to higher frequencies. Maybe it's coastal areas would be nice. I think at some point we know that the model is not very good at high frequencies, and I will show you more of that tomorrow. So we stop there. I guess the next runs maybe we'll go possibly to 1 Hertz, depends if we have how good the model is. We only use 24 directions. I know a lot of people now are using 36 or more directions. It actually makes the model a bit more expensive. At the coast, I think it can give better results, but globally, it's still not super clear that you get better results with more directions. It's just more expensive so far, so we're playing with that, probably with the new hindcast, with a European mesh. I guess we'll go to 36 directions, but first we have to validate that it actually works better. And then the big, there's many different ways to run the model, and you can change many parameters that are tuned. And so there's, in WaveWatch 3, there's 6 or 5 main options for defining how you compute the dissipation and generation of the wave by the wind. And they are called ST1, ST2, ST4, and so forth. And so actually we've developed this ST4 parameterizations. And so that's the one we use. And within this ST4, you can have slightly different flavors of that. And so the flavor we're using today is called Test 471. So they've been, we didn't actually do 470 tests, but we did quite a few hundred of them. And what we tuned on this is different ways to dissipate the swell, to generate the wind speed, to break the waves. And so every couple of years we come up with something a bit better. So this is a version from a couple of years ago. And for the Mediterranean, we still use something a bit different. Because this one has a bit of a problem that the growth of the waves at short fetch, when the waves start to grow, is a bit too slow. So in the Mediterranean, that's a problem. So we still use a setting which is a bit different from the global model. So that's for wave dissipation and generation. The other thing I didn't touch much is what's called the discrete interaction approximation, the DIA. That's the way to compute the nonlinear wave interactions. I will talk more in detail about that tomorrow. And then we compute the way the bottom friction, how the wave dissipate their energy by friction on the bottom. And so what we use now is in WaveWatch 3 is called BT4. It corresponds to effect of a movable bed. So if you have sand, the sand grains can move with the wave motion, and that makes ripples on the bottom, and the ripples change roughness, and the roughness then enhances dissipation. So that's what we've done. I know other people in other models have developed some seagrass specific dissipation stuff. We don't have that yet in WaveWatch, but in some regions that could be also important. But this bottom friction thing is in the coast, in some shallow water, it really makes a big difference. This is basically one example in one buoy, which is close to Ile-Dieu in France. The blue line will be the standard Jones swap parameterization, and the red one here takes into account the fact that there's actually rock outcrops there, so you have a flat region with full of rocks, which is presumably fairly rough and dissipation, and does more dissipation to the wave energy. And so the wave height is reduced, and you can see that one event with big swells with long periods where that's important. So what's available today? We have these different domains. We have this global grid, which is at half a degree resolution. And this grid is actually two-way nested with zooms, and this is in WaveWatch that uses a multi-grid system that you will learn about next week. So together with the global half-degree grid, we have this 6-minute grid for the Pacific coast, which is on the other side of the Earth, the Northwest Atlantic, which is this purple region here, and the blue one here is Northeast Atlantic. All these three are 6 minutes, so 1/10th of a degree. We also have a grid around New Caledonia and Vanuatu in the Pacific, and some other grids in French Caribbean. So all these grids are running together, and so right now we also have an Africa grid at 6 minutes, but we haven't done the hindcast with that yet. We only do forecasts, so at some point it's going to come. So yeah. So that's for the multi-grid system, and we have another multi-grid system for the Mediterranean with a MED at 6 minutes, and then we have a northern Mediterranean region around the French coast, 2 minutes, and then the grid in the Black Sea at also 6 minutes. And typically, this is the kind of result we get with this hindcast. So we use a lot of the altimeter data to validate. So this map shows you 1 year of model compared to the altimeter data. This is for the year 2012, I believe. And the colors tell you the root mean square error. So if it's less than 10%, it's blue. And in some places, it goes up to 30% or even more, and it's red. And what you see on this map is that there's quite a few places in the world ocean where the error is actually less than 6–7%. Like trade wind area where the wind is very steady. But there's still work to do around the ice edge where you have really large errors, presumably due to wave-ice interactions. And also in coastal areas, and there's many reasons for these different problems in coastal areas. One is that this model doesn't have any current. So if you look at it closely, you will see that you have this red band here with the Agulhas current, and the fact that we don't have that in the model. There's other things which are due to wind. The Somali current also is another issue, and the winds in coastal areas usually is a big problem. And also it's only a half a degree resolution model, so in places like the Red Sea or the Mediterranean Sea, you cannot expect miracles if you don't resolving properly the gradients. So what was done between the test 451 and the test 471, which was the latest update we did, the way we retuned the model, we improved a little bit the short fetch behavior of the model. So this map shows the difference of the error maps of the two. So when it's red, it means that the new model is better, and when it's blue, it means that the old model was better. So it's hard to make things better everywhere, I can tell you. So one place it got better is around the ice edge with some wave-ice interactions. That was the first version of that. We changed the shoreline reflection, which I think contributed to improving the results in Mediterranean. And the swell dissipation got things a bit better on one side of the Pacific, but not on the other side of the Pacific. And yeah, so that's the story of what we do. Now with the unstructured mesh triangles, so the hindcast, the 30-year hindcast we did was part of a project called Homer, which was done for marine energy purposes. And so we stored the frequency spectrum on the entire grid. So there's only 100,000 points. But we also store the full 2D spectrum on selected points, so there's a few thousand points with spectra. And the idea is to use that for various applications with marine energy. And so that was run for 93 to 2013, and that was extended recently for 3 more years, and so we're going to extend it again, and then they also extended it spatially in the coming 2 years, and it's what Matthias is going to work on. So yeah, and so if you want to get a feeling for what it gives, oh yeah, that's the old website. So now it's called marc.ifremer.fr. There you go. Does it work? So if you want to get a feeling for what it looks like, we also have this demo website with forecasts. You have the English version by just clicking on the English flag, results, and waves. And yeah, so for all those of you that want to go surfing this weekend, what do we get? Saturday. Well, we'll just ask Mikael, he will tell you.
No waves.
No waves this weekend? Pretty flat? Easterly wind? Yeah. So wind from the east, so maybe a little bit of swell. Yeah, like half a meter swell.
Maybe you can just show the spectrum.
And the spectrum. Yeah, that's what we expect for Saturday morning at 2 a.m. Yeah, so there's a bit of swell coming from the west here, this red blob. And then the wind from the east, which is making this wind sea here. So this spectrum is corresponds to this dot here where we have the buoy. But yeah, the total wave height is less than a meter, so the swell height must be half a meter or something like that. So really nice time for going to the beach. Maybe not for surfing. And this is a validation with the buoys. And even on top of that, the model is still overestimating from compared to the buoy. So yeah. So that's what we do, and that's I think that was the last slide I had. Let's go back to this. I guess I had some conclusion at the end. Let's go to the conclusions. So potentially there's lots of data, but probably not enough, since some of you are here to run your own model because you want to have your specific things, and that's very good. For buoy data, it still is very complicated, so we've done a lot of work as part of the GlobeWave project for validation of satellites to get lots of data together, but with that we stopped in 2012 or something like that, so we only have one part of the history record, and so CMEMS will take over that, and so these two people here will be part of this effort. In terms of models, there's many people have been running models, and some of them are better than others. So hopefully we'll try to explain you why some models are better than others, and that will be detailed tomorrow. And of course, I'm a bit biased, so I think our model is pretty good. I know some places not so good as some others, but in many places it's actually pretty good. And all of this requires a lot of tools for handling the data, so different formats. So now we work mostly with NetCDF only. We still have a few tools with ASCII files we're trying to get rid of. And so most of the work that needs to be done to be able to compare the model and observation is to basically work with the spectra. And that's what we'll do this afternoon. So I think that's, yes, that's all I have. Any questions on the database thing?